Is Kasper van der Vaart, and he is going to talk to us about segregation in avalanches.
Okay, thank you. Good afternoon, everyone. I'm very happy to be here and to have the opportunity to tell you about my research on size segregation on an inclined conveyor belt. Quasi-stationary because, well, it's stationary in the way that we look at it, but it's flowing. I performed this research at TPFL in Switzerland under supervision of Christophe Ancey and in close collaboration with Nico of the University of Manchester. Before we get started, I would like to show you this picture here. It's a short story. After I finally finished making the conveyor belt, I went to celebrate. I went to the Intertoys and bought all the marbles they had in stock. There was not a lot. I was disappointed, and I used them for my first test runs, and that's what you see here. So we're looking. I placed the camera in the belt on the lower part, and we're looking up, up along the belt, and you see all these large particles that are on the bottom, and all the way up there's just small particles. That's quite interesting, and that's what my talk is about. When we started with this project in 2012, there were three main objectives. The first was to reveal the internal structure of a segregating avalanche. The second, to test current segregation models. And the third, to investigate the so-called segregation mobility feedback effect. And today I will only discuss the first. For those of you who are not familiar with what size segregation is, I will briefly explain. It is an effect that occurs in granular flows that takes different sized particles and separates them into distinct groups. In the particular case of a free surface flow, an avalanche, all the large particles move to the front, to the top, to the free surface. And now, why is size segregation interesting to study? Is when we take an avalanche or a debris flow, this large material that moves to the top will then move to the front because the higher the top layers of the avalanche are moving faster, and a large particle front will form. Now, this large material can also move to the side and form lateral levees, and this is more a three-dimensional effect. That you will not see in the experiments I'm showing you today, because the setup is a bit more two-dimensional. And talking about setup, this conveyor belt, why a conveyor belt? What's wrong with a traditional channel? Well, we wanted to be able to study the flow and the segregation for a very long time. And with a traditional channel, you put the camera there and you have just a very short time window. The avalanche comes by, we see some segregation, but just a few seconds. And with the conveyor belt, you can just keep studying, keep filming and measuring indefinitely. And another advantage is that it's quite easy to reach steady state. Just turn it on and we wait till it seems steady. And then there's also the convenience that the vertical velocity distribution can have the same shape as in a conventional channel. That's what you see here. Now you see a schematic of the conveyor belt. The dimensions are 104 centimeters by 10 centimeters wide by 15 centimeters high. And the particles we used for the experiments are 40 millimeters for the large ones and 5 millimeters for the small ones. The angle is 19.8 degrees. The belt speed 72 millimeters per second, and the flow depth around 45 millimeters. And the region of interest is the lower right part of the belt, where we expect a large particle front to form. So all the experiments I will show are taken on this part of the belt, and the top belt we don't look at. I will explain in a minute why it's less interesting. The imaging technique we've used is a combination of refractive index matching and a laser sheet. And we use this technique because it allows us to take a cross-sectional image of the flow in the middle of the flow, far from the sidewalls, to sort of minimize, or where the sidewall effects are minimal. And it works as follows. We submerge the entire belt, this huge thing, in a ginormous aquarium, and fill it with a liquid that has the same refractive index as the particles. The liquid contains a fluorescent dye, and this fluorescent dye we excite with a very thin laser sheet. So we only excite it in a thin plane in the flow. And then the light emitted from the dye is detected with a camera, and because the particles don't have a dye in them, they appear as dark spots on a bright background. That's what you see here. So large particles and small particles, and here you see a part of the belt. Now, before I go on to the results, I would like to show you a movie so you get an idea of what is going on in this avalanche. And this is what I think is the most fun part. So we see that size segregation causes a large particle front to form. And this is, of course, at an angle of 19.8, but for convenience I put it straight. Behind the front, there is a very large region where there is remixing or segregation. And then behind this segregation region, there is the tail, which extends all the way to the end of the belt. So another 60 centimeters in that direction, there's just small particles. And occasionally, a large one will go a little bit further, but we will see in a minute that if we time average, all the large particles will remain in this region. When we look at the vertical velocity distribution, we can see that the top layers are avalanching down, and the bottom layers are being dragged upslope by the belt. And in the center, the speed is 0, and it is as if we, the observers, are running along with this avalanche at its mean velocity. And we can simply shift the velocity profile, and you get something back that's a bit more familiar. Now you might see that here in the front we have a small problem. There's a problem with the belt that we were not able to resolve before I came here. And that is the large particles at the front here, they tend to slip. And you see that best here. So the speed at the bottom is not 0. So what it does on the belt is that it slows down the large particles here, and it has some effect on the segregation in this area. So that's for future work. We hope to resolve this slip problem. Now, when we look at a small particle velocity field, the blue arrows indicate a downward movement, the red arrow is an upward movement, and the size of the arrow is a magnitude for the speed. We can see that segregation takes place over this entire region. So in this entire region, small particles move down. Not very fast, but they definitely move down. And the strongest downward movement is in this region here at the end, where where nearly all of the small particles go down quite fast. You can see the curvature of the field there. And then for the large particle velocity field, we see that the large particles go up here and here. Also this entire region here, there's upward segregation. But the strongest segregation is just right here after the front. And when large particles reach the free surface, they travel to the front and then move down again. And when they enter the segregation zone, they immediately move up 1 or 2 layers. These images are a second measurement where we place the camera a bit closer, so you get a higher resolution of the front region. And you basically see the same. I think it's very nice, this downward movement of the small particles, and here upward for the large particles. And this part here where a lot of the large ones go down is probably because these large particles here, there is some slip here, so the speed is not so fast. So a lot of them want to go down here. And with a time averaged particle concentration or volume fraction, we can clearly see the three distinct regions. The large particle front, here in black, where the volume fraction for the small particle is 0. Then we have this region here, where there is remixing. And then this point is where the tail starts, small particles, because the last large particle moves up here. We see that as soon as large particles are deposited on the bed, they segregate up to the center of the flow. But then we see this dark finger there. So apparently, large particles, when they reach the center of the flow, they stay there for a very long time, relatively, compared to when they go up a layer and then they move quite fast to the front. And that results in this finger here. And we see that the strongest segregation for the large particles is in this region, where most of the particles move up. If we zoom in a bit with a higher resolution measurement, we see this eye a bit better. And it appears that large particles that come in here and segregate, it takes a certain distance for them to move up here. So not all of the large ones go up here, most of them go up here. It's not really clear why. Now then we're nearly at the end. I would like to tell you the three most important observations that I think we can make from these measurements. The first is that, well, we can see these three distinct regions, the large particle front, the segregation zone, and the small particle tail. Then the fact that these large particles, when they segregate up to the middle of the flow, that they spend a relatively longer time there, traveling with the mean velocity of the avalanche, which is quite interesting, I think. And then that segregation speeds are a bit larger when closer to the front, both for the small particles and the large particles. For future work, we would like to improve the setup and remove this slip artifact. We want to compare the results with current segregation models. We want to study the effect of the angle and the speed, and to do some quasi 3D imaging with two sheets, or maybe a fast oscillating sheet, to get some three-dimensional imaging of the particles, and then finally to study the segregation mobility feedback effect. And with that, I'd like to end, and thank you for your attention.
Questions for Kasper? Yes. Sorry, I have a question. So you're putting this fluid in between the grains. Have you tested the same setup without the fluid, and does it influence the principles in the physical?
Well, the fluid is about the same density and viscosity as water. So, in the tests, well, the liquid lubricates a bit, and it reduces the noise. But I didn't see any changes in the physical behavior or the movement of the particles. And I must confess that it's quite difficult to study the flow when there's not the liquid, because then I can only look on the sidewall. And the sidewall, usually all the small particles want to stick to the sidewall. So that's difficult. But it's something, what I should do to see the difference with that. Thank you.
You mentioned that the slip at the front to you looks like something that's undesirable. However, it may very well be the real phenomenon. And so I was wondered whether you had a way of detaching the large spheres from the wall that you have at the end of your chute, and if so, would you not be satisfied to see again some slip if they were detached, or is it just a true artifact, as you mentioned?
Well, it's true. I'm not really sure if it's an artifact or not. I looked at a lot of measurements or movies or data from real avalanches, and I don't think that when a large particle comes to the front and it's overrun, then it's still moving very fast. It seems, okay, maybe it's stumbling, it's true. So, yeah, when I maybe increase the friction of the belt and I still see this slip, I think I would be happy. But when it's removed, it will also be very interesting. I'm not sure if it's real or not, if it's an artifact or not. But there's only, I have to find out.
Just to add to that, it might be that you're big particles because I'm just wondering if your asperities are the size of the asperities that you've got, or the friction, the amount of friction you've got on the base, might actually be, your small particles might be sticking quite happily, because at the front you've only got big particles. You will have perhaps a natural slippage because the asperity is relatively smaller compared to the size of the particle. Does that make sense? In other words, it could be real because your relative roughness is reduced because you don't have
the roughness of the belt is a bit limited by I have the small particles and the large particles, and if I make the roughness too much, the small particles will get stuck at the end of the belt. So there's an interplay there. But small particles, they never reach all the way to the front. So yeah.
So I'm just suggesting it might also be real from another perspective, just on the size of the roughness for your different.
Yeah, okay, I understand what you mean. Yeah. But I still want to try out if I can. It's just a simple matter of making maybe some more spaces on the belt so that the large particles also can fit in these holes. I think it's something I want to do.
I was wondering if the segregation phenomena is masked by a purely entropic drift, because you inject the big particles on the bottom and you extract them on the top. So there's just a diffusive drift going upward. That can happen even if you don't have segregation.
So why are then the large particles moving to the top before they reach the end of the belt?
Okay, but once the steady state is reached,
okay,
you were injecting big particles from the bottom.
Oh no, I'm not injecting any.
No, but in the video you see that they enter.
Ah, yeah.
By the bottom. So then there's just an entropic flux going up.
I think that once the steady state is there, it strengthens the effect. I think so, yeah. Once there is this large particle front, and large particles come in on the bottom after being deposited, it's much more easy for them to go up.
Yes.
Because there's a little bit less small particles and they're also moving very fast. So I think that once it has reached this steady state with the large particle front, it's easier to maintain. Because it takes about a minute for it to set in, but once it's there, it's never gone. Does that answer your question?
Yes, but then how can you? Okay, you cannot be sure that you measure a flux due to segregation just because of different concentration.
Okay. Sorry.
If it was purely entropic, then it would become uniformly distributed in the middle. So there would be some aspect of that, but then it would be uniform, and the rest of it would be uniform. So it wouldn't actually go completely clear.
Yes. No,
there's both effects happening.
Yes, I'm not saying that there's no segregation, but it can be masked by the
so you see both of them.
Okay, let's go ahead and thank our speaker again.